Section: Introduction. In this section, we discuss the importance of out-of-distribution (OOD) detection in real-world machine learning applications. When we deploy models, they will inevitably encounter inputs that differ from the training data. This can lead to incorrect predictions, ranging from overly confident to completely wrong. OOD detection helps identify these cases so that the system can handle them appropriately, such as notifying users or triggering further investigation. We introduce a new method called Hopfield Boosting for OOD detection, which builds on modern Hopfield networks to enhance detection performance. By using an auxiliary outlier dataset, AUX, we improve the model's ability to detect OOD samples by learning a boundary around the in-distribution (ID) data during training. Our contributions include proposing Hopfield Boosting, which leverages modern Hopfield energy for sampling weak learners and achieves state-of-the-art performance in OOD detection. We demonstrate significant improvements in false positive rates on CIFAR-10 and CIFAR-100 datasets. Previous work has distinguished between anomalies, outliers, and novelties, each serving different purposes in applications. We focus on detecting samples outside the training distribution and view sample categorization as a potential downstream task. Post hoc OOD detection methods, like maximum softmax probability (MSP), use statistics from classifiers to identify OOD samples. While effective, these methods have limitations as they should focus on the probability of the input data itself. Various post hoc approaches have been proposed to address these limitations, with some using modern Hopfield energy for OOD detection. Training-based methods modify the training process to enhance the model's OOD detection capability. For instance, self-supervised outlier detection (SSD) uses self-supervised learning for training. Outlier exposure (OE) methods, including Hopfield boosting, incorporate auxiliary data to improve OOD sample detection by refining the decision boundary between ID and OOD data. These methods have shown significant improvements over traditional approaches, highlighting the importance of utilizing auxiliary data for OOD detection. Section Summary. In this section, we introduce the importance of out-of-distribution (OOD) detection in real-world machine learning systems to handle unexpected inputs during deployment. We propose a novel method called Hopfield Boosting that enhances OOD detection by leveraging modern Hopfield networks and an auxiliary outlier data set to improve model performance. Our approach achieves a new state-of-the-art in OOD detection, surpassing previous methods by reducing false positive rates on CIFAR-10 and CIFAR-100 datasets. Section: Continuous Modern Hopfield Networks. In this section, we discuss continuous modern Hopfield networks, MHNs. MHNs are a type of associative memory networks that enhance traditional Hopfield networks by introducing continuous queries and states using a new energy function called MHE. The MHE enables MHNs to have a large storage capacity and allows for retrieval with just a single-step update. The update rule of MHNs aligns with the softmax attention mechanism used in the transformer model. Successful applications of MHNs include various tasks such as classification and OOD detection. We provide an overview of MHE for OOD detection in the upcoming section. For more detailed information on MHNs, please refer to the appendix. Moving on to boosting for classification, we delve into AdaBoost, which is an ensemble learning technique specifically designed for classification tasks. AdaBoost focuses on difficult-to-classify data instances by assigning them higher weights, similar to support vectors in support vector machines, SVMs. Other popular boosting methods include gradient boosting, logit boost, and LP boost. Next, we explore radial basis function networks, RBF networks, which are function approximators represented as a weighted linear combination of radial basis functions. These networks have been utilized as hypotheses for boosting in the past. When the linear weights in RBF networks are strictly positive, they can be seen as an unnormalized weighted mixture of Gaussian distributions. The connection between RBF networks and MHNs through Gaussian mixtures is further discussed in the appendix. In the method section, we introduce Hopfield Boosting, which involves formalizing the OOD detection task, providing an overview of MHE's suitability for OOD detection, and introducing the aux-based boosting framework. A summary of the Hopfield boosting concept is depicted in a figure. Considering classification and OOD detection, we address a multi-class classification problem and define OOD observations as those significantly deviating from the normal data generation process. OOD detection is formulated as a binary classification task using an outlier score derived from an encoder. The outlier score helps distinguish between in-distribution, ID, and out-of-distribution, OOD, samples. The modern Hopfield energy, MHE, is introduced, which involves the log-sum exponential function to compute the energy between a query and stored patterns in the memory of the MHN. The energy value indicates the similarity between the query and the stored patterns, aiding in OOD detection based on energy levels. Section Summary. In this section, we introduce modern Hopfield energy, MHE, for out-of-distribution, OOD, detection. MHE utilizes the log-sum exponential function to measure dissimilarity between a query and stored patterns, enabling efficient OOD detection. By adjusting the inverse temperature parameter beta, MHE can effectively distinguish between in-distribution and out-of-distribution data based on energy levels. Section: Boosting Framework. In this section, we use the Hopfield Boosting Framework to enhance our understanding of how to select informative outlier data. We employ an auxiliary, aux, dataset to help us learn the decision boundary between the in-distribution, ID, and out-of-distribution, OOD, regions during training. Similar to AdaBoost, Hopfield Boosting focuses on picking outliers near the ID-OOD decision boundary to train the model effectively. We consider samples near the decision boundary as weak learners, as they have neighbors from both their own class and the foreign class. A single weak learner may only slightly outperform random guessing, while combining multiple weak learners forms a strong learner. We represent the raw aux data instances as a matrix O(D) and the encoded aux patterns as O. The boosting process involves assigning weights to each data point in O(D), aggregating these weights into a vector W_T, and using them to draw mini batches for training. Hopfield Boosting introduces an energy function based on minimum Hellinger distance, MHE, to evaluate the strength of a specific learner. This energy function helps identify locations in the data space where the model's decision between ID and aux classes is uncertain. To update the weights W_T+1, we use the aux patterns as queries and compute their energies. These energies are then normalized using a softmax function to obtain the updated weights. By training with informative samples near the decision boundary, we aim to improve the detection of patterns outside the training distribution. In our approach, we train a classifier on the ID data using cross-entropy loss and incorporate an OOD loss using the aux data to refine the decision boundary between ID and OOD regions. The composite loss function includes a hyperparameter lambda to balance the importance of the OOD loss. Hopfield Boosting focuses on minimizing the energy function E_B, which is used for sampling weak learners. We create mini batches of ID samples and weak learners from the aux data based on the weight vector W_T. These mini batches are fed into a neural network to generate a latent representation. Our method involves using a linear classification head for the cross-entropy loss and a two-layer MLP for the OOD loss. The OOD loss is computed based on the latent representations of the sampled data instances. Hopfield Boosting calculates the OOD loss for each mini batch by evaluating pairwise similarities between patterns, determining the energy values of individual observations, and then aggregating them. Our approach leverages Hopfield networks in a novel way to train deep neural networks, offering a differentiable optimization procedure compared to traditional SVMs with an RBF kernel. Section Summary. In this section, we introduce how the Hopfield Boosting framework leverages informative outlier data close to the decision boundary between in-distribution (ID) and out-of-distribution (OOD) regions to train the model effectively. By sampling weak learners near this boundary and using an energy function to determine their strength, Hopfield Boosting enhances the detection of patterns outside the training distribution. The method involves training a classifier on ID data with a cross-entropy loss and an OOD loss using an auxiliary AUX dataset to refine the decision boundary, demonstrating the effectiveness of utilizing Hopfield networks in training deep neural networks. Section: Summary. In this section, we present an overview of Hopfield Boosting. Each iteration involves three main steps: weighting, evaluating, and updating. Initially, we sample a mini-batch from the ID data and adjust the AUX data weights accordingly. Then, we assess the composite loss on the sampled mini-batch. Finally, we update the model parameters and, every nth step, also update the sampling weights for the AUX dataset. We have created a video illustrating the learning process of Hopfield Boosting. For more details, please refer to the appendix. During inference, we calculate the OOD score S(SHE) using the full ID dataset and a randomly selected subset of the AUX data of the same size. This step incurs a slight computational overhead compared to a complete forward pass. We experimented with using a different scoring method, but the approach in the equation has proven to be more effective as it leverages information from both ID and AUX samples. This can be advantageous for handling query patterns that are dissimilar from both the memory patterns in X and O. We also compare Hopfield Boosting to two other methods, HE and SHE, which do not utilize AUX data for improving the boundary between ID and OOD data. Instead, they evaluate the MHE on ID patterns only to classify samples as ID or OOD. There are subtle differences between the methods, such as the number of Hopfield networks used for different ID classes. Furthermore, we provide two toy examples to illustrate the key concepts of Hopfield Boosting. These examples demonstrate how the weighting step helps in estimating the decision boundary accurately, even with a small number of weak learners. Additionally, we show how inliers and outliers influence the energy surface, resembling the scenario where some data points in the AUX set are more informative for OOD detection than others. In our experiments with CIFAR-10 and CIFAR-100 datasets, we train Hopfield Boosting with RESNET18 using ImageNet-RC as the AUX dataset. We evaluate the model's OOD detection performance on various datasets not seen during training, such as SVHN, textures, ISUN, places 365, and different versions of the LSUN dataset. We calculate scores using a specific equation and assess the model's discriminative power between CIFAR and OOD datasets using FPR95 and AUROC metrics. Model selection is validated on MNIST, ImageNet-RC, and noise-added datasets. Section Summary. In this section, we outline the Hopfield Boosting algorithm, which involves weight sampling from ID data, evaluating composite loss, and updating model parameters. At inference, we compute OOD scores using both ID and AUX data, with a moderate computational overhead. Comparing Hopfield Boosting to he and she methods, we show that our approach utilizes AUX data for better ID and OOD data boundary determination. Additionally, we provide toy examples illustrating how Hopfield Boosting's weighting step aids in estimating decision boundaries accurately, especially when dealing with large, uninformative data instances in the AUX set. Section: ImageNet-1K. In this section, we evaluated Hopfield Boosting on a large-scale benchmark using ImageNet-1K as our ID dataset and ImageNet-21K as our AUX dataset. We tested the performance of Hopfield Boosting on various OOD test datasets such as textures, sun, places 365, and iNaturalist by fine-tuning a pre-trained RESNET50 model. We compared Hopfield Boosting to 8 other OE methods, including MSPOE, EBO-OE, POEM, MIX-O, DAL, DEVO, DO, and DOS. Our experiments showed that OE methods generally outperform non-OE methods in OOD detection, which was consistent with previous findings. During training, we ran the network for 100 epochs for CIFAR-10 100s and 4 epochs for ImageNet 1K. In each epoch, the model processed the entire ID dataset and a selection of aux samples. We used mini batches of size 128 per dataset, resulting in a combined batch size of 256. We updated the model based on a composite loss function for each mini batch. The sample weights were updated after each epoch, and we only computed weights for 500,000 aux data instances for efficiency. Hopfield Boosting achieved state-of-the-art OOD detection results without the need for a similarity engine, even on large datasets like ImageNet 1K. We used SGD with specific hyperparameters and tuned the values of beta and lambda for each dataset separately to optimize performance. In our results, Hopfield Boosting showed equal or better performance compared to other methods, particularly excelling in the FPR95 metric for all OOD datasets. It outperformed POEM, the previous best OE method, across various datasets. Boosting weak learners significantly contributed to the performance of Hopfield Boosting, showcasing its effectiveness in outlier sampling. Overall, Hopfield Boosting demonstrated superior performance in OOD detection across different datasets, including CIFAR-10, CIFAR-100, SVH-N, and ImageNet 1K, showcasing its scalability and effectiveness in large-scale settings.